Hello, my name is Chris Garrett, and today I'll be discussing how learning can be applied to the problem of image segmentation. First off, I'll be discussing the image segmentation problem itself and why it's important. I'll then discuss how others have addressed the problem, and then talk about some of the really terrific resources available for studying it. I'll then finish up with a brief discussion on how I'd like to explore the problem. According to the Gestalt theory of perception developed back in the 1920s, there is a set of relatively simple functions that happen in our brain that provide the basis for the phenomenon of perception. The two most fundamental of these are segmentation and its counterpart, perceptual grouping. There is strong neurological evidence to support this view. Even with this insight, the problem of computer vision and perception is far from being solved. This is at least partly due to the fact that even the fundamental problem of image segmentation remains open. Building on the basic image processing techniques grounded in feature extraction, new learning techniques are beginning to bridge the gap by addressing the problems of context understanding and multi-scale information. Also notice how I've kept properly in quotes referring to the quality of the segmentations. The goal here is to segment an image on how a human likely would, which is very subjective to our view of the world. Here you see an example of what is meant by image segmentation for the purposes of human-like perception. This example comes from the Berkeley segmentation dataset, which I'll discuss later. What this shows is that given an image, this is how a human, averaged over a small population of volunteers actually, would segment the image on the left. Notice how humans focus on the objects in the image and not the details such as the zebra stripes. This particular example still proves to be problematic for computers today. Before we discuss learning, let's back up a bit and talk about some of the purely algorithmic approaches. These involve feature extraction and processing. These features may include things as simple as similarity between color or luminance, or primitives such as points, lines, or shape edges. They may even include patterns that define textures. Spatial proximity or orientation can also be used as cues for grouping regions in an image. Of the non-learning approaches, the two that stand out the most are the canny edge detector and the combined brightness color texture gradients method explored by Berkeley. The canny edge detector is in wide use in many image processing applications as it performs well and has robust implementations. The one drawback is that it is sensitive to scale and needs to be adjusted to the image. The other method is actually a combination of several. It is among the best performing of the non-learning methods, but doesn't appear to be in widespread use. I also should note that these methods by themselves do not completely segment images and must rely on other well-known methods, such as the Hopf transform, to fill in any gaps left behind. Learning for image segmentation is most commonly done with classifiers, and just like any learning classifiers, there are largely two different approaches. The discriminative methods, which are the most well-studied and remain the most common, and the generative methods, which are relatively newer and a hot area of research. Each of these typically operate on the same set of features as the non-learning approaches, but take training data into account either directly or indirectly. The same advantages and disadvantages of each also apply to image segmentation. Discriminative methods are generally easier to implement and understand, but lose information about uncertainty and often require that the classes be linearly separable in some basis. Generative methods are often more difficult to implement, but they have the distinct advantage of being able to model uncertainty about the classification. Most recently, hybrid approaches have been applied to show the most promise. Discriminative methods are typically applied in a bottom-up fashion to quickly analyze small-scale features. Generative methods are typically applied from the top down, as they can capture more abstract concepts such as recognition of object parts or semantic labels. There is evidence that this is how humans perform this task, thus supporting its viability. Arguably the most popular data set in use in this field is the Berkeley segmentation dataset. It includes several images that have been hand-segmented by human subjects. The latest version contains 500 base images, so that the combined color and grayscale totals 1,000. The set is well documented and has been used as the basis for doing detailed evaluations, also published by Berkeley, of several common segmentation methods. Here we see some of the evaluation examples. Berkeley has very nice metrics on recall and accuracy rates, but these pictures succinctly capture some of the issues with each method. The top row is the same image pair presented earlier. The bottom left shows the results of one of the best non-learning methods, and the bottom right shows the best overall method, which happens to include learning. While not perfect, the learning method does outperform the non-learning one, especially when it comes to dealing with textures such as the zebra stripes. Here are more results from the evaluation. Again, the learning method generally outperforms the non-learning one, but still, it falls short of capturing everything that a human would want to segment, such as the facial features on the person in the top row. Finally, here are some of the most challenging images that the set has to offer. Notice the variation in the human segmentation for the anemone in the bottom row. This highlights yet another challenge, dealing with the subjectivity of human input. The result is nearly useless segmentation using any current machine-based method. Image segmentation is a very hard problem that I'm anxious to explore. While I don't think I could compete with the best of breed evaluated by Berkeley, I do think I can at least outperform some of the non-learning methods. Using the Berkeley set, I plan to start by extracting features from the training data and use that to learn a generative model for segmentation. I believe that I can then use this model on a given input image to generate a map of relative likelihoods that a border exists at given locations. I believe that I can use this map to generate the most likely proper segmentation for an input image. I plan to start with a naive base to learn the model. Once I have that working, I then plan to move on to either try other classifiers or to extend the scale being examined via larger and more features or attempt learning a hierarchical model. For the final report, all learned models will be evaluated against the Berkeley results for accuracy and recall, thus concluding the project. Thank you for your time and attention, and good night.